Hi guys, in this video we're going to talk about the next part of application in dot product or cross product, which is projections. Okay, so let's see what is projections. So given two vectors A and B, we have A and B here with the same initial point P, right? So if S is the foot of the perpendicular from R, so we have this point R here and S perpendicular from it. Okay, so the on this line containing P to Q, which is also vector A, then the vector representation of P to S here is called the projection of B onto A. And it is denoted, right, the vector of PS here will be denoted as projection of B on A, like this. Okay, that is the vector, right? The vector of this projection is indicated by this. As for the magnitude or the length of this vector from P to S here is denoted by component of B onto A. Okay, so we are going to figure out on how to calculate the length of this projection, and later also we're going to figure out what is the vector of this projection. Okay, now to do that we are going to use the formula that we are familiar with, right? We have used it before, which is this formula. This is the formula that we have used before in looking for the angle by using the dot product, right? By using this formula we can also figure out the component, right? The component of this projection, or in other words the length. Okay, so if you look at this, to find the magnitude of the vector projection, they are using this, which is the magnitude of B, right, times with the cos theta, or the angle. Okay, so if you try to refer to this, you'll see that it become like this. So this is the formula of finding the magnitude. Okay, I'll just put it away a bit. Okay, right, this, if you try to rearrange this formula into this formula, you'll see that we can say that this formula of finding the magnitude of vector projection is also equal to this, which is the dot product of A times B, A dot B over the length of A. Okay, so basically, if you have an information of the degree or the angle, you can directly use this formula to find the length of the shadow or the projection of B onto A. Otherwise, you can use this formula to find the length. Alright, one more formula that you can use is this. The same is also extracted from this, right? We just move B outside the fraction, and you'll see that it become this dot B times, actually. So basically, what is this actually? What is this? So if you can remember, this is the formula of unit vector. So by using unit vector times with B, right, we can also find out the length. So all of this is known as the component of B, right? We have B onto vector A, right? So we have the component of B onto vector A. Okay, and next, so basically when you are looking for the length or the magnitude, it is known as the component of B onto A. And of course, after you find the component of B onto A or the length of B onto A, we might as well look for its vector. So to look for its vector, right, or in other words, the projection, right? This is the formula, right? To look for the projection, we are going to multiply the component that we obtained before, right? Which is this, right? So basically, right, excuse me on the name there. So it is a projection of A onto B, and the formula is actually this component right time with the unit vector of A, and this will give you the new vector for that projection. Right, now let's try to look at, maybe just directly look at the exercise here. We have three vectors given, A, B, and C. We have three vectors. So first, they want us to calculate and find a scalar projection and vector projection of A onto B. Okay, so basically, if they are saying scalar projection, meaning they want us to find the component of A onto B, or the magnitude of A onto B. As for the vector projection, they want us to, after finding out the scalar projection, give them the vector of that projection. Okay, so we have here vector A, right? Is on exactly on the plane, and then we have vector B. Okay, so we want to look at vector A onto B. So we can't really, look exactly how to look at it because of the we are looking at 3D chart right now, but we can get the idea. We want to look for the projection of A onto B. In other words, it should be, the projection later should be 90 degree. Right? This projection should be this projection of this A here, the projection later should be onto this line of B, this vector of B, right? But it should later be 90 degree, right, when you compare it with the original A. Right? So let's do the calculation. Okay, first, scalar projection of A onto B. So to find the scalar projection or the component or magnitude, we are using the formula of component of A onto B. So we can you can choose either of these way to calculate, but the easiest or the direct formula that we can use to just plug and calculate is this. Okay, because we don't have the angle just yet, so we can just use this one. Right, so I'm using this. So AB, so the dot product of AB over with the magnitude of B. Okay, so this is the calculation. The dot product with the magnitude, and you get 5 over 14 as the length. So you can try to calculate what is the value later, but it will be around this figure. 5 over 14 will be the length of the shadow of the projection later. And what about the vector? So the vector will be calculated by using this again. So component, this component that we calculated just now, 5 over 14, will be multiplied with the unit vector of B, where that is where the shadow is, right? Is on the vector B. So the unit vector of B multiplied with the component of 5 over 14. So this is how we multiply it, right? Because before that, we'll find the unit vector of B. So like this, right? We have covered this before. So to find the unit vector of B, we are going to divide the vector of B with its magnitude. So this is what you get. And then multiply them to get the new vector. This is the vector. Now let's see, is it really the vector? Right? Is it really the vector? Is this really the projection of A onto B? Okay, so we have A and B, and we want to measure, is it true that the vector that we have just now, right, 15 over 14 negative 5 over 14 10 over 14, is it really will be on this vector B and will be perpendicular to A? So after I plot it, and this is what I get. Okay, so basically, as you can see, right, this is the new vector or the projection of A onto B. We might not be able to really look at it exactly as we want to look at it, because it is a 3D, but we get the idea. You get the idea, right? This is the projection, and we know that the length is 5 over 14, just like we calculated before, and the magnitude, the vector is as what we have I showed you before. Alright, so let's look at the next one. Now they want us to find the same thing, scalar projection and vector projection, but now it's not A onto B, A onto C. In other words, right, this is A onto B just now, so let's just change it. Now we have A and C. This is C. So now they want us to find A, the projection of A onto C. So as B before, it should be along this line. Right? So let's do the calculation. Okay, so A onto C. Right? First, let's calculate for the magnitude. So by dividing between the dot product of AC with the magnitude of C, where the shadow is, right, where the projection is. So this is what we get. The length or the magnitude is 8 over 5, and then let's find out the vector. So to find the vector of A onto C, we'll need to multiply between the magnitude or the component with the unit vector of C. So this is how we calculate the unit vector of C. So we'll get this as the unit vector. So multiply them together and we'll get this. So let's try to plot it into our graph to see whether is it true that it is the vector, the projection of A onto C. So we have A and C here. So we expect the projection to be along this line, maybe around this area, right? So where is the projection? Let's try to plot it down. Okay, so that is it. That is the vector projection of A onto C, right? So this is how you look at the projection. Thank you.